जी, screen visible है?
Yes, sir.
Okay, so let's start that numerical. A rigid tank contains 5 kilograms of refrigerant 134A. So a rigid tank, we already know, a tank whose volume will be fixed, that the volume of that tank cannot be changed. So delta V will be equal to 0. That is the meaning of a rigid tank. So a rigid tank contains 5 kilograms of refrigerant 134A, the substance which is placed inside this tank is R134A, a type of refrigerant, right? Initially at 20 degrees Celsius and 140 kilopascal. So initial temperature is 20 Ti and initial pressure T1 or P1. The refrigerant is now cooled, so it means heat is removed from this refrigerant while being stirred. So it means, yeah, because stirrer भी है, which is making this refrigerant to be stirred, and heat is removed from this refrigerant. So now we have a constant volume tank whose temperature is dropping because heat is removed, right? So what will happen to pressure? Because here volume is fixed and temperature is dropping. So what will happen to pressure? Because we already know from Boyle's law, for a constant mass, PV is equal to a constant, right? So it means when the pressure is at constant temperature at T is equal to constant, right? That is Boyle's law. Similarly, we have Charles' law when pressure is constant, and mass is constant, then V is directly proportional to temperature. So V over T is equal to a constant. But now in this case, so here in Boyle's law, temperature is constant, in Charles' law, pressure is constant. But here in this case, volume is constant. V is equal to constant, right? So in this case, when the temperature will drop, pressure will also drop, right? So here pressure is directly proportional to temperature, right? So here when the temperature will drop, so it will make this pressure to drop also because the refrigerant is now cooled, volume is fixed. Cooled means heat is taken out, means temperature is dropping while being stirred until its pressure drops to 100 kilopascal. So it means the final pressure is P2 is 100 kilopascal. Determine the entropy change of the refrigerant during this process, because during this process heat is removed from this refrigerant. So, and we know from the definition of entropy that entropy change is given by del Q by T, right? Delta S is equal to del Q by T. So here heat is removed, means this term will be a negative. So heat is removed, so entropy of this refrigerant will drop. But at the same time, heat is added into the surroundings. So entropy change of the system plus entropy change of the surroundings, when you add them both, that will always be a positive number. But entropy change of only system, in this case, is dropping because the heat is leaving the system. So when heat is lost by a system, that is actually a negative quantity. So that was the schematic diagram. I already roughly drawn here. So that is the schematic. That is the mass, substance type, initial temperature, initial pressure, heat is being removed. And to increase the heat transfer, we also use a fan, right? For example, in your refrigerator, there is no fan, but in your air conditioner, in the inside unit, right, or the outside unit, which is releasing heat, the condenser, there is a fan. To increase the heat transfer rate, we use a fan. Right? So we shall see this, the function of this fan or the increase of heat transfer due to this motion of fluid in the subject of heat transfer. Okay. So now we need to calculate the change in entropy, means delta S. And this delta S, we may write it as M into, because the final entropy minus initial entropy. That is something which we need to calculate. All right. And we know entropy change we can calculate from this equation del Q by T. And in the last lecture, we have discussed how this del Q by T is evaluated. Either you have to integrate or whatever. So, and then these entropy values are tabulated in in the form of some table. For example, for steam, if it is a water, then you have to see the steam table. Now it is not water here, it is refrigerant 134A. So we can calculate these or we can see these values of entropies from that table of refrigerant 134A. So, so this is what we need to calculate change in entropy using this formula. So it means we need to calculate first S1 and then S2. What is S1? Entropy at initial state, or initial state by what is given? Pressure, initial pressure, and initial temperature. So at this pressure and temperature, we need to calculate entropy, which is S1. So how we can find from the tables, not steam table, it is R134A table. But first of all, we need to be sure what is the state of this refrigerant at this pressure and temperature, whether it is in superheated region, in the mixture region, or in the liquid region. Once we know that at this pressure and temperature, the region where this substance lies, so from that region, from the table of that region, we can find its entropy. So let's go to the, for example, superheated steam table or saturated steam table. We can find out what is the state of our substance at this pressure and temperature. So let me show you the table. So here is the steam table, superheated steam table, because there is no UF, HF, HG. So here for this pressure 0.14 megapascal, हमारा pressure भी कितना 140 kilopascal और megapascal में that is 0.14 megapascal, that is T set. And this pressure T set is minus 18, very low. And what is our T? That is 20 degrees Celsius, which is greater than T set. So it means that substance at this pressure and at this temperature is superheated. So that R134A is in the initial state of this R134A is superheated. Right. So we have to see that table of superheated steam at 20 degrees Celsius. Here are the values of thermodynamic properties, specific volume, internal energy, enthalpy, and entropy. And we are now interested in entropy. So that is our required value. So S1 is 1.0624 kilojoules per kilogram per Kelvin. And V1, or specific volume, we have also seen here. Here is V, 0.16544. All right. So S1 and V1, we would need V1. Let's see why we need V1. So that is S1. Now we have calculated S1. Now we need to calculate S2. So for S2, we have to see what is the final state. So at final state, what is given? Pressure is given, P2, 100 kilopascal, right? And what else is given for state 2? Any other thermodynamic property which is given for state 2?
No, sir.
Okay, so then how we can find out S2? Because only pressure is given. We need to know at least one more thermodynamic property to trace a point, right? So now here is what is given, that is a rigid tank. So it means during this process, when heat is transferred, volume of that substance does not change. That was given. V is constant, means V1 is equal to V2. This V1, which we have calculated at initial state, this V1 will be equal to V2. V2 is equal to V1. Right, so at point 2, volume is also given, which is equal to V1. Because during this process, this volume of that substance does not change because it is placed in a rigid tank. All right. So now V2 is given and P2 is given. So P2 is equal to 100 kilopascal and V2 is equal to V1. Now with the help of these two, we can find out, we will try to find out the S2. So we need to find out S2, the entropy. But again, just like here, at initial state, first we determine whether it is in superheated mixture or liquid region. Here we again need to find out because here a cooling process occurred. So during this cooling process, there is a possibility that this substance enters into liquid region because when you cool something, its phase may change from gas to liquid. So maybe this second state is in mixture region, or this second state is still in gaseous region, only temperature is dropped. Or maybe it is in liquid region. So all these possibilities may exist. I can show now on TS diagram these thermodynamic properties. Right. So this was the initial state that was in the superheated region. Let me show that is P1 pressure, and this was temperature 20 degrees Celsius. And at this pressure, saturation temperature was minus, I think 18. So check. That was minus 18.77. So it means this temperature inside the room at this pressure of P1 was minus 18.7. So this was initial state, state 1. Now its temperature is dropped at constant volume. Right, so there are constant volume lines on this ES chart. Constant volume lines are like this one, and then they shift like this on TS diagram. This represents, because from this point, some constant volume line passing. At this point, there is certain V1, right? So it means, for example, this line represents a constant volume line passing through this point 1 at this pressure and at this temperature. And now this is the constant volume line curvature in the superheated region, and this curvature shifts like this inside the dome. That is constant volume. So now what happened here, volume remains constant and temperature drops. Pressure also drops because there are a number of pressure lines are passing. This is pressure line, this is another pressure line. So pressure is dropping from this point 1 till this. Now we don't know where is point 2. Maybe point 2 is here. Outside the dome, only temperature is dropped. Maybe point 2 is here. Maybe point 2 is here. Or maybe is somewhere here. It becomes liquid. This whole line represents a constant volume line because volume remains constant during this process. Pressure is dropping, temperature is dropping because it's a constant volume cooling process. Constant volume cooling process. Now we need to determine first where is point 2 with the help of these two thermodynamic properties which are given. The pressure is 100 kilopascal. For example, this line, ये जो dotted line है, that is 100 kilopascal line, for example. So on this line, there is a possibility that this point is here, here, or maybe here, right, on the same volume line. तो वो ही अब हमने find करना है. So how we can find out when pressure is given, volume is given. Again, chapter 3, the concept of chapter 3, the concept of chapter 3. It's all about chapter 3. So for a given pressure and for a given volume, how we can find out the exact location of the substance in the gaseous, in the mixture, or in the liquid region. Pressure is given, volume is given.
सर किसी और थर्मोडायनामिक प्रॉपर्टी को मतलब फाइंड करेंगे कॉरस्पॉन्डिंगली फ्रॉम टेबल.
कौन सी प्रॉपर्टी? ओके, ये देखिए 100 किलो पास्कल के ऊपर दिस इज द वॉल्यूम. नाउ इसी 100 किलो पास्कल पे, फॉर एग्जांपल, लेट मी शो इसे सेपरेटली शो करता हूँ. यस डायग्राम. This is 100 kilopascal line. Now this volume, V2, which is equal to V1, it could be here, here, anywhere on this pressure line. So from the table, what we can find out? We can find out these volumes. Because at 100 kilopascal, this Vf is a fixed value. This Vg is a fixed value. So if at 100 kilopascal I see Vf and Vg from saturated table, and then I compare these volumes with this given V. So if our given V is greater than Vg, it means we are in the superheated region. If our given V is less than Vg and greater than Vf, it means we are in the mixture region. If our given V is less than Vf at that pressure, then we are in the liquid region. That's how. This is something which we have learned in chapter 3. Okay, so let's see. So it means, first of all, I need to check at this pressure of 100 kilopascal, what is Vf and what is Vg. So how can I do it from the table of R134A, which table? Saturated table, not superheated. Superheated metal, at this pressure, there are a number of possibilities of V's. But at this pressure, within the dome only, these are the two properties. These are the two possibilities. Within the dome, at this particular pressure, this Vf and Vg are fixed. So let's go to the table. Saturated refrigerant 134A for a given pressure, because pressure is given. Pressure is 100 kilopascal. So at this pressure, what is Vf and Vg? Here are the Vf and Vg values. Now let's compare it with our given Vf and Vg. What is given 100 kilopascal and what is V1? 0.1654. And we have seen from the table Vf is this one, Vg is this one. So where is this value between these two? This V1 is greater than Vf, but this V1, which is equal to V2, is less than Vg. So it means it is somewhere here in this region within the dome. So it means during this cooling process at constant volume, when pressure is dropped from 140 kilopascal to 100 kilopascal, and temperature is also dropped, but temperature kitna drop hua? Temperature is dropped till this saturated temperature. क्योंकि हमारा जो point था, initial pressure was 140, for example, this is 140 kilopascal line. This was P1, 140 kilopascal line. This was 0.1 in this superheated region. Now 0.2 is here somewhere in the mixture region, which we have just seen. So it means there will be a constant volume line like this one. It is following a constant volume line, and this is 0.2 in the mixture region. Right, so that is the TS diagram of that question. Okay. So exam may first you have to draw a schematic with all the energies crossing the system boundary, and then you will be asked to draw a TS or PV diagram. Right, so here is the TS diagram of this question. This is point 1, this is point 2. Pressure is dropping, temperature is dropping, but it is following a constant volume line, and these are the constant volume lines. जो हमने last time देखा था TS diagram पे how the constant volume lines look like. तो वो आपने just roughly draw कर. So now one thing is clear that this point is in the mixture region. So now what to do? Now we have to use the equation of mixture region to find out S2, because purpose here we are trying to find out S2 entropy at this point too. So it means now we can, so at this point two, first we need to calculate X2, because point 2 के ऊपर entropy find करने के लिए we have to use the equation, mixture region equation, which is SF plus X SFG. Right. So here we need to find out X. And here S2 is also unknown. So there are two unknowns. So it means we need to calculate this X from some other equation. So other equation is this one, because we know what is V2, which is equal to V1, is equal to V2F plus X2 V2FG at 100 kilopascal. This is point 2. Right. So just values put kar dein. Here is the V2F and V2G. And V2 is already known, which is equal to V1. So values put kare, so from here we can find out X2. So here is the quality or dryness fraction at this point. So we use it here in this equation to find out S2. S2 is equal to S2F plus X2 S2FG. So just values put kar. What is S2F and S2FG? इसी प्रेशर के ऊपर 100 किलो पास्कल पे, and let's go to that table again. 100 किलो पास्कल, here are the values of SF and SG. SF and SG ये यहाँ यूज होंगी, SF and SG, और X2 हमने फाइंड कर लिया 0.859. so just values put करें, so that is S2 0.8278 kilojoules per kilograms per Kelvin, because we are calculating for 1 kilogram of mass. In those tables, all these values are for 1 kilogram, 1 kilogram, 1 kilogram, 1 kilogram, right? Everything in these tables and charts, all these values are given for 1 kilogram of a substance. So now S2 is calculated, S1 was already calculated. So now we can find out the change in entropy, M into S2 minus S1. These S are small symbols, right, for 1 kilogram of mass. This values put in total mass is 5 kilograms. So the total entropy change comes out to be itself, it comes out to be a negative number, right? That was S2. Entropy was dropped because heat was leaving that system. So this entropy change is negative, minus 1.173 kilojoules per Kelvin. Because when heat is lost by a substance, it goes to a more stable state because it becomes a more cooler, it becomes more stable. Molecules are not vibrating as much as at high temperature. That's why the randomness or disorderness in the system or in that substance decreases. That's why its entropy decreases. But at the same time, this heat is going somewhere, where this heat is going into the surroundings. So surrounding is absorbing this heat. So here the entropy of the surroundings will rise because here the randomness or disorderness on this side, the surrounding side will increase. So if you add the delta S of system, and similarly, if we find out the delta S of surroundings, and then when you add these two entropy changes, these two entropy changes will always be a positive number. That was the increase of entropy principle. But वो हमने यहाँ find नहीं करना. Here the requirement was just to find out the entropy change of on the system side. Our system is losing heat, so that's why entropy is dropped or decreasing. That's why it is a negative number. Okay. ये मैंने TS diagram already explained कर दिया, but here what is how it is drawn in the book. That is your book is simple. उसने एक line draw की है, बाकी ये जितनी explanation है ऐसा कुछ नहीं है book में. So that's why the lecture is so important that you can understand the meaning of this line clearly here. So now let's solve one more problem related to entropy. Calculate the entropy change of the universe as a result of the following processes. Entropy change of a universe. Universe means that space which is isolated. So this is our universe. Right? And we know in this universe there are infinite number of processes are occurring. So we are now asked to find out the entropy which is produced or entropy which is changed due to these three processes. So there are infinite number of processes are occurring in this universe. And now we are asked to find out the entropy change of this universe due to these three processes. So what is the first process? First process is a copper block of 600 grams mass and with Cp of 150 joules per Kelvin. What is this Cp? Specific heat, but it is not written joules per kilograms per Kelvin. It is written joules per Kelvin. It means this Cp is for this whole mass, 600 grams की total Cp दी हुई है. 1 kilogram substance का Cp नहीं given इस question में. That Cp with a capital C means for the whole mass, right? So for this whole, so here if you write mCp delta T or and if you multiply this m with this Cp, that will be wrong because this Cp which is given is not for 1 kilogram. Here there is no kilogram in the denominator. It is joules per Kelvin. It means it is for this whole mass. So what is this value? That is actually m into Cp, m into small cp, which is equal to capital Cp. That is given. A copper block. So a copper block है इस यूनिवर्स में ये तीन प्रोसेसेस हो रहे हैं. What is the first process? There is a copper block of 600 grams. So this mass given है a certain mass of 600 grams and Cp of 150 joules per Kelvin, and its temperature is given. Its initial temperature is 100 degree Celsius. That is its initial temperature, T1. Is placed in a lake at 8 degrees Celsius. Now it is placed in a lake. And what is the temperature of this lake? 8 degree Celsius. Now this is a process which occurred in the universe. Okay. किसी ने ये copper block initially at 100 degrees Celsius, now it is placed in this lake at 8 degrees Celsius. Now a process will occur, and we know what is the process, the heat transfer process. It will lose heat, and at the same time lake will absorb heat. So this, due to this process, what is the entropy which is generated in the universe? That is part A. So it means we need to calculate the entropy change of this copper, because now there are this on the system side we have copper. So we need to find out the entropy change of this copper. Plus we need to find out the entropy change of lake. The surroundings is lake in this case. And then we have to add these two entropy changes. So the net entropy change, the total net entropy change will be delta S of universe will be equal to, due to this process, is equal to entropy change of these two. Entropy change of copper plus entropy change of lake. In दोनों को हम add up करें. So that will come out to be a positive number. If it comes out to be 0, then it means this process was fully irreversible. If this entropy change, sum of entropy changes comes out to be negative, then it means this process is impossible. This process cannot occur. But we know this process definitely will occur. We know from our experience and from our observation that we can cool copper using such process. If we dip this copper in the lake, this process will definitely occur. So that's why this entropy change of universe should be or must be a positive number. And there is a heat transfer, and heat transfer process is an irreversible process. Chapter 6 में हमने study किया. Heat transfer process is an irreversible process when delta T approaches to 0. ठीक है, so यहाँ delta T to, sorry, when delta T is something higher than 0. If delta T, अगर ये भी 100 पे होता और ये कहीं 100.0001 पे होता, then delta T approaches to 0, and then it approaches to a reversible process. But here we have a significant delta T. So it's not easy to reverse this process. When you try to reverse this process, we have to use some artificial means to reverse it, जिसकी वजह से surroundings में कोई permanent change आता. तो ये chapter 6 में हमने already discuss कर लिया. So here we need to find out the entropy change of the copper plus entropy change of lake. So what is the entropy change of copper? And we know how we can calculate entropy change. Entropy change, जो उसकी general definition है, because we do not have tables of copper जहाँ से हम S2 और S1 of copper को find करें, right? So that's why we need to calculate entropy using that equation del Q by T. Okay. Right. So that is how we can calculate entropy change of copper. But here temperature is changing. Temperature is not constant. 1 से लेके 2 तक. Okay. If I'm talking about only copper, delta S of copper, ये उसकी general equation of entropy change, integral 1 to 2 del Q by T. And temperature is changing. Copper का temperature कहाँ से कहाँ तक change हो रहा है? 100 degrees Celsius is the initial temperature. So ये जो T1 है, this 1 is actually equal to T1, which is equal to 800 degrees Celsius. What is T2? What is the final temperature? इसको हम integrate करना है from T1 to T2. T1 is 800. What will be T2? What do you think? Sorry, 100 degrees Celsius है, 800 नहीं है, 100. जी. What will be T2? Any idea? This copper is placed in a lake. जी.
8 degrees Celsius.
8 degrees Celsius.
8 degrees Celsius, right. ठीक है जी. After some time, its temperature will be equal to the temperature. So T2 is 8 degrees Celsius. Okay. So that is the equation with limits. So we have to calculate this entropy change from this initial state, 100 degrees Celsius, to final state, which is 8 degrees Celsius. That will be an entropy change of copper. Now, very important thing is equation where you see single T, it's not delta T. So ये जो temperature है, that should be in kelvins. So it is 373 Kelvin, and that is 280 Kelvin. So ये जो आपने इसको integration perform करनी, that should be from 373 to 280 Kelvin. Right. Now what is del Q? How we can find out del Q? जो heat loss हुई है, heat lost by copper is given by m of copper, small Cp of copper into delta T. That is the heat lost by copper. And m into Cp is equal to capital Cp. That is given 150 joules per Kelvin. Right, जी, I hope this equation is clear और ये solution में mentioned. So delta S of copper is equal to mCp dt. Differential change है ना, differential change dt divided by t, because we need to integrate this equation. जी जी.
सर एक क्वेश्चन था, ये जो सीपी है ये सी के साथ है, तो ये हमने राइटिंग से में चलेगा, ये कैपिटल सी लिखा हुआ है या कोई और भी होगा हमें? अब हम इसको मैथ के साथ मल्टीप्लाई करके एमसीपी कर सकते थे सर,
लेकिन फिर स्मॉल सीपी
राइटिंग में क्लियर नहीं
देखिए,
होता.
स्मॉल सीपी गिवन होना चाहिए था ना, या तो स्मॉल सीपी गिवन ही नहीं है, कैपिटल सीपी गिवन है. अगर स्मॉल सीपी गिवन होता है उसे आप मास से मल्टीप्लाई करते हैं और उससे कैपिटल सीपी या डायरेक्ट यहाँ पे एमसीपी यूज करते हैं. इट मींस कि ये जो क्वेश्चन है इसके अंदर 100 ग्राम्स यूज ही नहीं होना, बिकॉज 600 को स्मॉल सीपी से मल्टीप्लाई करके ये फाइनल आंसर दिया. इस क्वेश्चन में यही थोड़ी सी कंफ्यूजन है.
ठीक है सर,
यही मिस्टेक करेंगे, वो एमसीपी को मल्टीप्लाई करेंगे विदाउट सीइंग द यूनिट्स. यूनिट्स में कहीं पर किलोग्राम नहीं आ रहा. मींस दिस सीपी इज नॉट फॉर 1 किलोग्राम. ओके जी. सो एमसीपी इज गिवन. That is now the equation which we need to integrate. That is a constant m into Cp. That is capital Cp. ये यहाँ ऐसे लग रहा है कि कैपिटल नहीं, that should be a small Cp per kilogram. m अगर आप m के साथ मल्टीप्लाई करके लिख रहे हैं. So mCp, which is equal to capital Cp, that is given, that is 150 joules per Kelvin, and that is a constant. वो आपने outside the integral लिख दिया और इसको आप integrate करते हैं, log of t, limits apply करते हैं, and that is clear hopefully. ठीक है. और इसका final answer. So you will see the answer will come with a negative number by itself. आप खुद negative यानी put करेंगे, that will be come out to be a negative number. Log of this will be a negative number, and that is minus 42.48. Of course, copper is losing heat, so its entropy will be dropping. So that is the entropy change of the copper. Similarly, now we need to calculate the entropy change of lake. अब जो heat transfer हुआ lake, तो equation वही होगी lake के लिए भी. General equation delta S is of lake is equal to delta Q by T. अब यहाँ del Q नहीं लिखा. Why? It is not del Q divided by T. यहाँ पे तो del Q divided by T और इसको आपने इंटीग्रेट करना पड़ा था with dt. Delta T नहीं, यहाँ dt है because you have to integrate. T was not constant. What about the lake? The lake, जब heat transfer होगी to the lake, will the temperature of lake rise or not?
No, sir.
No, of course, because lake has a huge or infinite MCP product compared to the MCP of copper. So it means the temperature of the lake will be constant. So that's why there is no need to integrate, because this temperature is constant at 8 degrees Celsius. 8 degrees Celsius means 280 Kelvin. Single T, always Kelvin. व्हाट अबाउट डेल्टा क्यू ऑफ लेक कैसे फाइंड करें? लेक का तो एमसीपी भी नहीं गिवन, डेल्टा टी भी उसका अप्रोचेस टू जीरो।
सर जो डेल एस सी यू है सर वो पॉजिटिव 42.48 किलो जॉल देगा।
कौन सा?
सर ये
एमसी,
कॉपर
बिल्कुल, एग्जैक्टली। सो जो कॉपर ने हीट लूज की है दैट इज एक्चुअली गेन्ड बाय द लेक। सो वो हमने ऑलरेडी कैलकुलेट कर लिया, एम सी पी डी टी, एम सी पी डी डेल्टा टी ऑफ कॉपर, राइट? सो व्हाट विल बी सी पी डेल्टा टी ऑफ कॉपर, सी पी ऑफ कॉपर इंटू डी टी। और ये हमें डी टी हमें ना कॉपर का टेम्परेचर चेंज हो रहा है फ्रॉम दिस टेम्परेचर टू दिस टेम्परेचर, दैट इज गिवन। सो एग्जैक्ट टेम्परेचर चेंज हमें नॉन है कॉपर का फ्रॉम 100 टू 8। सो यहाँ पे आप सेल्सियस भी यूज कर सकते हैं। सो राइट, Cp of copper, so that is the heat lost by the copper which is gained by the lake. So this delta Q of lake is actually the heat lost by the copper divided by the temperature of the lake, which is constant 8 plus 273. So that comes up to be a positive number. Delta S entropy change of lake. दोनों entropy changes को add कर दें. So that is a positive number, 6.63 joules per Kelvin. So during this process, this is the entropy which is generated. This process is irreversible. That's why the entropy change is positive. Due to this process, there is some entropy is generated in the universe. Then that is a positive coordinate. Now let's see second case. Second case में क्या? The same block, means the same copper block at 8 degrees Celsius is dropped from a height of 100 meter into the lake. Same copper block is now dropped from a height of 100 meters into the same lake. Now this is a second process. So now we need to determine the entropy change during this process. So again, we need to calculate the entropy change of copper and entropy change of lake. So in this case, what will be entropy change of copper? Entropy change of copper. General equation by del Q by T. Now during this process, on the copper side, is there any heat transfer? Assuming कि यहाँ उसने air friction के बारे में कोई बात नहीं की होगी, so it means कि we are neglecting air friction. So if we neglect air friction, will there be any heat transfer?
No, sir.
No. All right. So if there is no heat transfer, it means delta S of copper is 0. Right? Because entropy की जो equation है, that is del Q by T. And during this process, there is no heat transfer because इसका temperature वही है 8 degrees Celsius. इस case में, second case में, the same block at 8 degrees Celsius. इसका भी temperature है 8 degrees Celsius. So temperature change is 0. So there is no heat transfer. Now what about the entropy change on lake side? Will there be any entropy change on the lake side?
No, sir, कोई change नहीं होगा.
कोई change नहीं होगा. So it means अगर delta S of copper भी 0 है, delta S of lake भी 0 है, दोनों को add करें तो total entropy change is 0. It means it is fully reversible process. हमने एक fully reversible process achieve कर लिया. It means this thing. But actually, all the actual processes in the universe are irreversible. Now let's look closely on the lake side. When this copper will hit the lake, जी
सर ये हमने इसलिए assume किया कि जो लेक का टेम्परेचर 8 है और ब्लॉक का भी 8 है, तो सर
ओके, लेट्स सी, वही मैं एक्सप्लेन कर रहा हूँ आपको. देखें, जब ये कॉपर विल हिट दिस लेक, what will happen? ये जो energy थी, that energy was mgh, with which it strikes this lake. यही mgh half mv square में convert हुई and it strikes this lake. When it strikes this lake, energy will be transferred to lake. ये जो copper ball की energy है, that will be transferred to lake. But in what form? Here it was a form of work, maybe you can say, because there was no heat content in it. But when it transfers its energy to the lake, and there will be some vibrations which will be produced inside this lake due to this hitting of this copper ball. What is this energy? Is it energy change at microscopic level? Molecules of lake will be moving faster due to this energy transfer from this copper to lake or not? एक energy produce होगी ना within this lake, right? So this energy, which was equal to mgh, now it is transferred to lake, and I am saying this energy which is transferred to lake, it is in the form of energy, internal energy. The internal energy of the lake will rise. This energy which is transferred to lake, that will be actually will rise its temperature. But because this lake has a huge mcp, we cannot sense this rise in temperature. But actually at molecular level there will be some rise in temperature, but because of very high mcp, we cannot sense this rise in temperature. There will be temperature rise of, for example, 8.00001 degrees Celsius. This energy is transferred to the lake, and within the lake, the molecules of this lake has moved apart from each other, because it is not a solid lake, it is a liquid lake. Liquid molecules can move, solid के तो molecules move नहीं करते हैं. They can only vibrate when temperature rises. So here there will be some vibrations produced inside the lake, and that will increase its internal energy. But with the rise of this internal energy, the temperature change is very, very small, which we cannot sense because MCP is so large. So that's why I would say that there is del Q on the lake side. And what is this del Q? That is the energy which is transferred from the copper इस फॉर्म में, और कॉपर की एनर्जी क्या थी, mgh. ये एनर्जी थी ना इस पॉइंट के ऊपर, which is actually transferred here to the lake, अगर हम एयर फ्रिक्शन को नेग्लेक्ट करते हैं. Otherwise some of it would have been lost here to overcome the air friction. So I would say that heat energy in the lake is actually this energy of the copper, which is transferred to lake, and temperature of the lake is constant. It's not changing. It is 80 degrees Celsius, right? Isn't it okay or not? Does it make any sense to you? So delta S of copper is equal to 0, but delta S of lake में एक energy transfer हुई है. ये जो work energy थी, that is converted into heat. At molecular level, molecules are moving. When they are moving, it means they are when their movement increases, it means its temperature will rise. But why temperature is not rising? Because the high MCP, high thermal, very, very high thermal capacitance. So it means temperature will remain constant, but some energy is transferred from work to heat to this lake. Right, see, mgh over 2 mgh of copper 0.6, 600 grams, kilograms 9.81, 100 joules, 100 meters, joules per Kelvin. So that is 2.04094 Kelvin. So now we can find out the entropy change for this process. So इस process में भी entropy change है, and that is 2.09. That is very small compared to previous case. Previous case में that was 6.63 entropy generated because of the heat transfer with a temperature change on the copper side, significant temperature change on the copper side. Here the temperature is constant and at a very low temperature, so entropy generation is very low. Right, Z, so that was part B. Now let's see part C. Two such blocks means the same two copper blocks at 100 and 0 degrees Celsius are joined together. Right. So now we have two such blocks. Same copper block is now joined with another such block. Actually, दोनों is same size. So it is like this. One is at 100 degrees Celsius, other initially at 0 degrees Celsius. Now two such blocks are joined together. So of course there will be a heat transfer. It will lose heat, it will absorb heat. And after some time, दोनों का mass same है, दोनों का Cp same है. So after some time, what will be the final temperature of this block? 50. And that will also be 50 because both have same thermal capacitance, same mass. So final temperature will be 50 degrees Celsius. But here the temperature is changed from 100 to 50. Here temperature is changed from 0 to 50. Here temperature drops, here temperature rises. Now this is a process. Due to this process, what is the entropy generated? So it means we need to calculate the entropy change of block 1 and entropy change of block 2. So this is, for example, 1. This is block 2. And we know entropy change is given by MCP ET, और दोनों cases में will be में general form में लिखता हूँ del Q by T. Here temperature is changing. एक केस में ये 50 से 100 हो रहा है, right? Plus दूसरे केस में the same del Q by T, and that is changing from 0 degrees Celsius to 50 degrees Celsius, right? But we have to convert it into Kelvin, so plus 273. Sorry, ये 100 से 50 पे जा रहा है, तो initial है, that is 100, final is 50. जो block 1 है, उसका temperature change हो रहा है from 100 to 50. So this is starting point, this is final point, 100 to 50. Or second block के case में the temperature is changing from 0 means 0 plus 273 to 50 degrees Celsius means 2 plus 273. And what is del Q? From the copper के case में we already know it is Cp, capital Cp is given into dt. So यही equation यहाँ लिखी हुई है. Cp, which is a constant, capital Cp, which is this one, dt by t, and what are the limits? 373 to 323. 373 to 323, 50 plus 273 into dt by t. Similarly for second, Cp into dt by t, what are the limits? 273 to 323, right? So आप integrals evaluate कर लें. Cp, which is 150, into log of temperature, or limits apply करते हैं, फिर negative rule use करें of the logarithm. So 150 log of Tf final temperature minus T1 initial temperature, or Ti. Similarly 150 log of Tf T2, ये जो T2 है for second case. So limits apply करते हैं, values put करते हैं. So here is the entropy change, the total entropy change of the universe, which is equal to entropy change of block 1 plus entropy change of block 2. So entropy generation during this process is 3.638. Right. So here again, of course, we know this process from our general observation will occur in reality. And that's why entropy change is not 0, and it is not less than 0 or negative. अगर आप कोई किसी ऐसे प्रोसेस को यहाँ पे इवेल्युएट करें which we know it is impossible to occur, and then if you calculate the entropy change, it will come out to be a negative number. Okay, so that is actually the second law of mathematical interpretation of second law of thermodynamics, that the entropy change during any actual process will always be a positive number. Entropy, whenever we say entropy change, it doesn't mean only on the system side. On the system side plus on the surrounding. एक system है, दूसरा surroundings है. So entropy change of both, the summation of entropy change of both will be positive number. So now there is a term which is called isentropic process. In thermodynamics, we know what is isobaric. जी
सर
question.
हमने जो पीछे वाला जो क्वेश्चन किया है उसके अंदर दो ब्लॉक्स थे, सेम कॉपर बॉक्स हैं, एमसीपी दोनों का सेम है, एक एंटर हुई है और एक से रिलीज हुई है। तो सर इसमें जितनी रिलीज की है दूसरे ने एब्जॉर्ब कर लिया है, तो सर इसमें सराउंडिंग का क्या काम? वो तो हम एज्यूम करते हैं वो मतलब कि उसमें हीट नहीं जा रही, तो सराउंडिंग में कितनी हीट चली जाती है सर?
सराउंडिंग सही नहीं, इसमें सराउंडिंग क्या है? फॉर एग्जांपल ये जो कॉपर 1 है इसे मैं सिस्टम कह रहा हूँ, तो सराउंडिंग्स क्या है? कॉपर 2, राइट? इस केस में जो आपका सिस्टम है वो आइदर 1 है या 2 है। अगर 1 है तो 2 सराउंडिंग्स है, अगर 2 है तो सराउंडिंग है। इसमें सराउंडिंग कॉपर ही है।
सही है सर।
ठीक है, वो जो सराउंडिंग का मतलब सिर्फ एटमॉस्फेयर नहीं होता, वो डिपेंड करता है एप्लीकेशन टू एप्लीकेशन। सराउंडिंग का मतलब कुछ और भी हो सकता है। इस केस में हमने एटमॉस्फेयर के इफेक्ट्स को नहीं इंक्लूड किया। अगर वो भी इंक्लूड करें तो एंट्रोपी चेंज विल बी, बिकॉज सारी की सारी हीट कॉपर 2 को नहीं जाएगी, कुछ हीट यहाँ पे भी ट्रांसफर होगी इनटू द सराउंडिंग्स। देन यू हैव टू ऐड डेल्टा एस ऑफ कॉपर 1 प्लस डेल्टा एस ऑफ कॉपर 2 प्लस डेल्टा एस ऑफ सराउंडिंग्स, जो एम्बियंट जिसे आप कह रहे हैं, दैट विल इवन बी अ बिगर नंबर।
जी
ठीक है, वो हमने नहीं इंक्लूड किया। ओके
ठीक है।
Okay, so next topic is isentropic process. We know isobaric process, we know isochoric process or isometric process. We have also uh, learned about or also the isothermal process. Similarly, now there is a term which is called isentropic process. So isentropic process is any process in which the entropy remains constant. Entropy does not change. If we say if there is any process in which entropy changes exactly 0, means S2 is equal to S1. That is known as isentropic process. Although there is no actual process which is fully isentropic, but we can use this assumption in some cases to simplify our mathematical model. जो हमारा mathematical design है, using this assumption becomes quite simplified. वो अब हम स्टडी करेंगे। सो दी डेफिनेशन ये थर्मो 2 में जब हम प्रैक्टिकल एप्लीकेशन स्टडी करेंगे, then you will see what is the use of this term S2 is equal to S1. So we are assuming if entropy change is 0, just like when we say temperature T1 is equal to T2, then it becomes isothermal process. When P1 is equal to P2, it is isobaric process. When V1 is equal to V2 during any process, if we say this V1 is equal to, that is isochoric or isometric process. Similarly, if entropy changes 0, then it is called isentropic process. Now, which processes, real processes, can be assumed isentropic? ये question है, which process where we can use this assumption? Can we use this assumption here in case of boiler, जिसमें heat add हो रही है 1 से लेके 2 तक? Is it possible to say that delta S approaches to 0? Because entropy changes, calculate हम कैसे करते हैं? What is the mathematical form del Q by T? और यहाँ तो Q transfer हो रही है. So we can never say that delta S equal to 0 for such process, for heat transfer process. Similarly, in case of condenser, where heat is lost, again delta S cannot be assumed 0. So जो भी heat transfer processes हैं जहाँ पे delta T is not 0, because यहाँ heat transfer हो रही है, यहाँ इसका कोई low temperature 20 है, here we have a very high temperature, for example 1000. So huge delta T is available here. Delta T is positive. So whenever we have a positive delta T and heat is transferred, it can never be assumed as an isentropic process. So heat transfer process can never be isentropic. ठीक, because यहाँ तो purpose ही heat transfer करना, और heat transfer होने से into the system or out of the system, the process can never be isentropic. हाँ, सिर्फ only in the case of Carnot heat engine, वहाँ पे जो हमने heat transfer की थी, if you remember, जो हमने chapter 6 में पढ़ा था, that heat was transferred into that into this gas जो expand कर रही थी, शुरू में heat transfer process था. Here we assumed TH, and here we also assumed TH. We assumed this heat transfer in case of Carnot heat engine taking place at constant temperature. System or surrounding, दोनों का temperature same है and heat is transferred. Of course, that is not possible in reality. That's why that concept of Carnot heat engine is just a theoretical concept. There we had assumed that this heat transfer was isothermal heat transfer, and that type of heat transfer was assumed isentropic only in that Carnot heat cycle. Because यहाँ जो heat transfer हो रही है वो delta T approaching to 0, so that is fully reversible. ठीक है, fully reversible means delta S. So only in Carnot heat engine the heat transfer processes can be assumed as isentropic, but not in real boilers or condenser or any other heat exchangers. This isentropic assumption cannot be used. Now let's look some other applications like turbine. Turbine में क्या हो रहा है? Fluid in हो रहा है, fluid out हो रहा है, and here work is transferred, and I insulate this turbine. This is a turbine. इसे मैं fully insulate कर दूँ so that there is no heat transfer to the surrounding. I can make such a turbine where heat transfer approaches to 0. And then if I make such a smooth turbine, such a perfect design that the friction, ये जो shaft move कर रही है into some in this bearing, the friction between shaft and bearing is assumed negligible. इतनी perfect lubrication है या इतना perfect contact है कि there is no loss of energy in the form of heat due to friction. और ये जो fluid hit कर रहा है to this buckets or turbine blades, again the friction between turbine blade and fluid is, for example, negligibly small. Right? Only in that case that ideal turbine can be assumed isentropic. So here in case of turbine where the purpose is only to transfer work, not heat, ये purpose ही नहीं है, and we want to reduce this heat transfer as much as possible in the turbine or in the pump reverse हो रहा है, pump में भी ये हो रहा है, we are giving work and we want that this work is used to raise the pressure or kinetic energy or potential energy. We do not want this work to be converted into heat. Okay. Here, the purpose is to reduce heat transfer as much as possible. Here again, in case of turbine, what are turbines and pump? These are work transfer devices. Let's see another example of nozzles. Nozzle may be purpose क्या है, to increase the velocity or kinetic energy. Diffuser का purpose क्या है, to decrease the velocity or to increase the velocity को decrease करें, pressure को rise करें. यहाँ पे क्या है, nozzle में क्या हो रहा है, pressure drop हो रहा है and velocity is increasing. And if we insulate this outer surface of nozzle, it means we are making this Q heat transfer with the surroundings approaching to 0. And here again, the friction between this fluid and the walls of the nozzle. That is a perfectly smooth surface. That this friction is also approaching to zero means Q approaching to zero. So here, these are the practical devices where uh, we can use this assumption of isentropic. Although it is not fully isentropic, there will be some heat transfer, there will be some losses due to friction, which is the source of heat, right? So, but at least ideally, we want to have such a turbine, we want to have such a pump, we want to have such a nozzle or diffuser. So in these engineering devices like pumps, turbines, nozzles, diffusers, actually they are adiabatic in their operation. Adiabatic means we want that there is no heat, there should be no heat transfer with the surroundings. And we want to reduce the frictional effects as much as possible. So here, where there are no irreversibilities. What are these heat transfer, friction? These are actually irreversibilities. So here we can say that fluid is entering. Ideally, we can say that fluid is entering at entropy S1 and it is leaving at the same entropy S2 is equal to S1. So then it is known as isentropic turbine or isentropic expansion. Here, pump में या compressor में it is entering with fluid is entering with entropy S1, leaving with entropy S2, which approaches to S1. Then it is known as isentropic process, isentropic compression process, where no entropy is generated. Why no entropy is? Because there no heat is generated, no irreversibilities. So the concept of isentropic is used to design these systems. First, we assume ideal situation, and then we implement the real or frictional effects, real situation. So it makes our design process easier if we use this assumption. तो वो हम थर्मो 2 में throughout will be using this concept. जब हम turbines पढ़ेंगे, nozzles पढ़ेंगे, compressors पढ़ेंगे, we will be using that term isentropic. We will be assuming that this process is isentropic, then we will design it, and then we shall include the frictional effects at the end to make our mathematical model and easier, or mathematical calculations or design calculations easier with this assumption of isentropic. But we can never use this isentropic assumption in these heat transfer devices. That should be clear. We cannot use, or we can never use this assumption in heat transfer processes, because heat transfer process में तो heat transfer हो रही है, so it can never be isentropic. Right, जी, जितनी भी मैंने so now on TS diagram, let's discuss one more thing. It is TS diagram. एक हमने PV diagram study की थी, pressure versus volume diagram. If there is a process which is isochoric, means volume remains constant. So how we can represent it? This is 0.1, for example. This is isochoric process because area under this curve is 0, just a point. That's why there is no work done on PV diagram. And that is isochoric process. What will be isobaric process? It will be like this one, because pressure remains constant. That is isobaric process, this one. This is isobaric, this is isochoric. Similarly, when we say it is isentropic process, means entropy does not change. So how we can represent it on PS diagram, it will be a vertical line because entropy is on x-axis, 1 to 2. So there is such process during which temperature is changed, pressure may be changed, but there is no irreversibilities, no heat transfer. So that ideal or that theoretical or imaginary process is isentropic. And isentropic process on TS diagram will be exactly vertical. Right. For example, ये जो turbine का process है, इसमें fluid enter हो रहा है 1 पे, 2 पे out हो रहा है. So ये 1 पे enter हुआ at high temperature if it is a steam turbine, leaving at a low temperature. यहाँ कोई high pressure था, ये कोई low pressure है. But it is isentropic. यहाँ पे कोई volume था, low volume था, here high volume है. So V1, this is V2, this is T1, this is T2, is point against, and this is P1, this is P2. But what is constant? What we have assumed constant? Entropy. We are assuming that jitni bhi fluid energy thi, that was fully transferred into work, and when it leaves, there is no entropy generated. During this process, inside the turbine, no energy of this fluid is converted into heat or lost in friction. So इस Q का मेजर जो भी पोर्शन वर्क में कन्वर्ट हुआ है, उसमें कोई पोर्शन फ्रिक्शन का नहीं है. There is no irreversibilities. So such process is known as isentropic process, and that is represented by a vertical line. Right, ये सब कुछ एक्सप्लेन किया हुआ है स्लाइड के ऊपर. It will be easier to understand. ये सब मैंने यहाँ points explain कर दिए. So now you know what is meant by isentropic process. Now let's move further. Entropy further discuss करें. Now we know entropy is given by this change in entropy is given by del Q by T. In other words, we are saying that del Q, or the heat transfer during any process, is equal to ds into T. Right. So it means heat transfer is equal to change in entropy into temperature. Just like we know work transfer is given by P dV. During any process from 1 to 2, we have to evaluate this integral. Similarly, to find out heat transfer during any process 1 to 2 is 1 to 2 T ds. So जिस तरह हमने वर्क ट्रांसफर में पढ़ा था कि एरिया अंडर एनी कर्व ऑन PV डायग्राम, क्योंकि प्रोसेस में एरिया अंडर दिस कर्व represents work transfer. Process one. All right. जी, कोई क्वेश्चन?
सर की आवाज नहीं आ रही.
हाँ, ओके. अब आ रही है?
यस सर, अभी आ रही.
ठीक. So this was PV diagram. On PV diagram, for any process between 1 and 2, the area under this curve represents work done. Similarly, for heat transfer, we can have temperature versus entropy diagram. So on TS diagram, area under any curve represents heat transfer, for example, because यहाँ पे temperature change हुआ है. This is from 1 to 2. Here is the temperature change, and here is the entropy change, right? So this side representing the temperature change, and this side is representing the entropy change. Just like here, this side is representing pressure change, and this side is representing volume change. So to calculate this area, we have to integrate this equation, or this equation of this line P dV from 1 to 2. Similarly here, to find out the heat transfer, because T into S product, so P into V product gives work done, temperature into entropy change product gives heat transfer, right? So that's why we use TS diagram to calculate or to estimate heat transfer, and PV diagram to estimate work transfer. So for example, there is some process on TS diagram. So if this is a differential change, right? During this process, that is the temperature T, and here is the entropy differential change in TS. So this del Q can be written as T into ds. Okay. To find out the total change over this whole line, we have to integrate it from this initial point 1 to final point 2. 1 to 2 ds. So just like here, if you remember in chapter 4, we need to know how pressure is changing. Pressure as a function of volume should be known. Similarly here, how temperature is changing during this process. If temperature is not constant, अगर the pressure constant हो, if you remember, then it was simply P naught, इसे आप outside लिखते हैं, and it is dV. That is work done. Similarly, अगर यहाँ पे temperature constant हो, if it is an isothermal process like boiling or condensation, then that will be constant into simply ds हो जाएगा, S2 minus S1. But if temperature is changing, then we should know how temperature is changing as a function of entropy. Just like here, we should know how pressure is changing as a function of volume. उस equation of that curve or line. Similar concept है जो PV के केस में था. The same is applied here for the case of DS diagram. So ये सब यहाँ explain किया हुआ है slide के ऊपर. You can read and understand. Isothermal process. Isothermal process is internally reversible. हमने chapter 6 में already पढ़ लिया है. At least from the system side, if temperature is constant, then the entropy, the heat transfer for an internally reversible process is equal to T naught into delta S. Units kilojoules, because heat transfer for small for 1 kilogram of mass, kilojoules per kilogram, or ये जो S है capital, that will be small s. T naught into, if temperature is constant, then T naught. If temperature is not constant, then we have to evaluate this integral. Right, see, this concept hopefully is clear now. Let's move forward. ये मैंने already आपको explain कर दिया कि isentropic
सर आपकी
process
आवाज कटने लग पड़ी है
on a TS process. आवाज कट रही है, कोई इशू नहीं. अब रिकॉर्ड तो हो ही रहा है, तो बाद में आप रिकॉर्डिंग सुन सकते हैं. रिकॉर्डिंग होपफुली ऐसा कोई इशू नहीं होगा. ओके जी. So this is TS diagram. On TS diagram, this isentropic process will be exactly vertical line. Then we also discussed in the last lecture, there is one T versus S diagram. There is another diagram which involves entropy, and that is HS diagram, जो हम thermo 2 में use करेंगे इसको, HS diagram, enthalpy versus entropy diagram, right? अगर isentropic process है, इस पे भी there will be a vertical line, और that isentropic process doesn't mean कि enthalpy change नहीं है. Enthalpy change हो रही है. That is, this vertical line represents enthalpy change, delta H. But if there are no heat transfers, there are no irreversibilities, then it is isentropic. Like a turbine. Turbine में, here is H1, here is H2, and work is done. So if it is fully isentropic, then from 1 to 2, entropy remains constant, S1 is equal to S2, but enthalpy changes, because this enthalpy change, H2 minus H1, is actually equal to work done. और जितना mass से multiply करते हैं, that is total, because a certain amount of mass is entering and leaving. So enthalpy is changing. So that's why HS diagram is very easier. You do not need to calculate this H1 and H2 from steam tables. You can directly read these values from such HS chart, because उसमें जो y-axis है, that is enthalpy. So, but actually there will be some entropy generated 1 to 2 process, because entropy generation means some energy is lost in the form of heat. यहाँ कोई heat transfer हुई है. So in HS chart, now you can see if some entropy is generated, heat is lost, heat is produced and then lost to the surroundings. It means कि यहाँ से कुछ heat loss हो रही है. So that's why there will be some entropy change from 1 to 2. Enthalpy भी change हो रही है. Delta H, the x-axis and y-axis, and the x-axis represents the presence or the change in entropy. Right. So this is HS chart and TS chart. So ये हम यूज करेंगे, अभी हमने सिर्फ just इसको understand करना था what is meant by isentropic process and how enthalpy could be changing during such processes. अभी सिर्फ हमने TS diagram और HS diagram पे just an overview है, जो इसकी real application है, that is something we will do in thermodynamics too. Okay. Now, still, the question is, what is entropy? Entropy जो हम स्टडी करते हुए आ रहे हैं उसकी जो एक मैथमेटिकल फॉर्म हम करें, that is del Q by P. It means whenever there is a heat transfer, heat production. What is heat production? Heat production, I am saying it is disorder form of energy or disorganized form of energy. Disorder form of energy. So whenever there is this disorder or this disorganized form of energy, that represents entropy. That is one way of saying entropy or to interpret entropy. So entropy can be assumed as molecular disorder, is a measure of molecular disorder or molecular randomness. So as the system becomes more disordered, जितनी ज़्यादा उसमें disorder होगा, so the position of molecule, for example, ये हमारा कोई system है which consists of a large number of molecules in it, which are continuously moving around in every direction. As there is a heat transfer into the system, this disorder will increase. Right? For example, ये एक molecule है. When the disorder increase, this molecule, it is difficult to guess its position. Maybe it is here, maybe it is here. In the next instant, it is here. In the next instant, it is here. So higher is the disorder, higher is the probability of this molecule to be at this position will drop, will increase. Right? So the position of molecules will become less predictable. You cannot predict its location as the disorder. Maybe this molecule is here, and the very next moment it is here, and the very next moment it is here. And what about the solid? Solid ke case mein molecules are not moving. They are mostly they are vibrating. So in case of solid, we can say the entropy is least in solid and highest in gases. Right? So entropy of a substance will be lowest in case of solid and it will be highest in case of gases. So because at microscopic level, when we view this substance at microscopic level means from the point of view of statistical thermodynamics. Entropy is actually how we relate entropy. It is the total number of possible microscopic states of the system. Total number of microscopic states means maybe this molecule is here and the next moment it could be here, it could be here. So there are infinite number of microscopic states possible for this system. Right? So the total number of possible microscopic states of that system is known as entropy with reference to statistical thermodynamics. So with reference to statistical thermodynamics, entropy is defined as this one, a log of, from microscopic point of view, we use this equation del Q by T, but from microscopic point of view or from the point of view of statistical thermodynamics, entropy is given as a log of P, where K is this constant, Boltzmann constant, and what is P? P represents the probability, right? Or the probability of those molecules to be at one particular state. Is related to the total number of possible microscopic states of that system called thermodynamic probability. It could be here, it could be here. The total number of possible microscopic states of a substance, of a molecule in a substance, is known as thermodynamic probability. So they use this such equation or to calculate, and then they have a method to calculate the thermodynamic probability. So that is a different field altogether or different way of calculating entropy at microscopic level. और ये हमने explain कर दिया, discuss कर लिया in the solid phase, the predictability to have this substance at one particular state or the predictability of a molecule is very much easier to find out. So that's why entropy is less. So as the disorderness increases, entropy increases. That's how we can understand entropy in a different way. So as the temperature approaches to zero, because as the temperature drops, so your substance will change from gas to solid. If the temperature drops to 0 Kelvin, absolute zero, so that at that point we can say that the entropy is totally zero. If we have a pure crystal substance, crystalline substance is something where the molecules, atoms, or ions of that which are made up of for that material is an extremely regular pattern in three dimensions. That is called known as crystalline substance. Right. So macro state is refers to the state of the system as a whole. Right. The quantities, for example, like pressure, volume, and temperature are macroscopic. It is difficult to describe the microscopic states of a system practically because of the large number of molecules involved, right? So for a given macro state, for a given temperature, pressure, and volume, a large number of micro states may be possible. That's why this is a different field to study a substance at microscopic level, and that is known as statistical thermodynamics. So here, with reference to entropy of a substance will approach to zero if temperature is approaching to 0 Kelvin. Right? And that is the third law of thermodynamics. Entropy of a substance could be zero only if its temperature is zero. A pure crystalline substance at absolute zero temperature is in perfect order. There is no disorderness. So we can say entropy is zero. That is known as third law. Third law of thermodynamics. इतना कोई practical उसकी relevance नहीं है. That's why we do not quote it in practice, because it is only about something which is related to absolute zero, which is not achievable practically. So that's why third law of thermodynamics को बहुत ज़्यादा refer नहीं करते in reality, because it is only saying that the entropy of a substance will be zero when it's in totally ordered state. No disorderness at all. Let's further analyze the concept of entropy. For example, let's make a different example here. For example, here we have some gas and we are adding heat to this gas. And if we have this paddle wheel or stirrer inside this gas, now no matter how large is the kinetic energy of these molecules, जितनी मर्जी इनकी kinetic energy आप increase करके by adding heat, this gas will not make this wheel to rotate, this paddle wheel to rotate. Why? Because the gas molecules, the energy which they have, it is highly disordered form of energy. The heat energy which we are supplying to this gas, it is a disordered form of energy. That's why maybe the number of molecules which are trying to rotate it clockwise is equal to the total number of molecules which are trying to rotate it in anti-clockwise direction. So it is a highly disordered or disorganized form of energy. It means entropy is very high. That's why we cannot get any useful work out from this system. Right? So disorganized energy does not create much useful effect. Disorganized high energy means very large entropy. Now, if we compare it with this case, right? What is happening here? In the absence of any friction, if there is no, this is a shaft which is moving, which is movable, and it is attached to this weight, which can be lifted up or down. So in the absence, so for the time being, if we neglect friction, raising a weight by rotating this shaft does not create any disorder if we neglect friction. And therefore energy is not degraded during this process. So it means in this case, when shaft is rotating, it means all the molecules of the gas of this shaft are actually moving in one particular direction, not like here. यहाँ पे भी हम heat add कर रहे हैं to the molecules of the gas, but the molecules of this gas are not moving in one particular direction. All of the gas molecules are moving randomly in every direction, right? So that's why here this is a more disordered state. Here it is more ordered state. When this shaft moves, all the molecules are actually moving in one particular direction. So here we have a more ordered form of energy, or this work. So, and that energy which is transferred is known as work. So it means work is free from disordered or randomness, right? Or in other words, it is free from entropy. Okay. So no entropy is transferred during this transfer of work. Here only work is transferred if we neglect friction. Some of the work will be lost to overcome friction, but that is very less compared to this case. Here everything is due to heat. Right? Here we are trying that this heat will create work using this manner, in this manner. That is not possible. That's why we have to devise a different type of system, different type of heat engines where we convert heat into work in a different way. उस हीट को पहले हम ऑर्गेनाइज्ड फॉर्म में लाते हैं इन द टर्बाइन और देन इट इज कन्वर्टेड इनटू वर्क और वहां पे भी वो टोटली वर्क में कन्वर्ट नहीं होता बट लाइक दिस यू कैन नेवर कन्वर्ट हीट इनटू वर्क डायरेक्टली राइट सो हियर वी हैव अ डिसऑर्डर्ड फॉर्म ऑफ एनर्जी इट इज ऑर्डर्ड फॉर्म इट कैन इजीली बी रिवर्स्ड इसको हम रिवर्स भी कर सकते हैं ये वेट जब दोबारा डाउन होगा दिस शाफ्ट कैन मूव इन द reverse direction, right? So here it is more reversible compared to this one. Okay, so that is the concept of entropy. इसको यहाँ से भी आप explain कर सकते हैं. Here you can see this pedal wheel when it moves and it does work on this. So यहाँ पे आप work transfer कर रहे हैं from the pedal wheel to the gas. But this work is now converted into a more disordered form. Now, this disordered form of energy cannot be recovered, and this process cannot be reversed. That is more irreversible process because here ordered form of energy was converted into disordered form of energy. That's why it is not. It is very difficult to reverse this process. इसको आपने reverse करना है, we have to use a heat engine. और heat engine में भी ये सारी की सारी energy reverse नहीं होगी because that work is converted into heat, and this heat cannot be fully converted into work. That is second law of thermodynamics. Work is converted into heat, but heat cannot be converted back into work fully. That's why it is irreversible, because during this process, entropy is generated. Disorderness is increased. Right? So the overall conclusion, बाकी जो भी डिटेल है मैंने एक्सप्लेन कर दिया है स्लाइड्स में, बुक्स में डिटेल में लिखी हुई है, आप वहाँ से पढ़ लें. Overall, what is the conclusion? Quantity of energy is always preserved. जितना आपने work supply किया, that is equal to heat. So quantity of energy remains preserved or constant during any actual process. That is the first law of thermodynamics. But the quality decreases. That is the second law. Because quality energy is converted into low quality energy because it cannot be reversed. So during any process, quantity remains constant, but quality definitely drops, which is the second law of thermodynamics. Quality drop means entropy is generated, right? So decrease in quality simply means more increase in entropy or molecular disorder will be produced. Decrease in quality is always accompanied by an increase in entropy, and that is called molecular disorder is produced. ओके जी, अब जो नेक्स्ट टॉपिक है इसकी मैं आपको वीडियो शेयर कर लूँगा. दो वी हैव सम टाइम, लेकिन मैं आपको टाइम देना चाह रहा हूँ फॉर दोज स्टूडेंट्स हु वांट टू अपीयर इन दी क्विज. तो ये TDS रिलेशंस हैं और एक न्यूमेरिकल ट्रिक है इस चैप्टर का। मोस्ट शेयर अ वीडियो ऑन इट, वीडियो लेक्चर, उसमें ये कवर हम कर लेंगे और नेक्स्ट जो वीक है उसमें सिर्फ चैप्टर 8 को जितना कवर हो जाएगा उसे हम कवर करेंगे। ये जो नेक्स्ट टॉपिक है एंट्रोपी का, दैट इज वेरी इंपॉर्टेंट। ठीक है, ये जो हम TDS रिलेशंस पढ़ेंगे with respect to exam point of view and also with respect to thermodynamics too. This is very, very important topic. इसके बगैर हम thermodynamics you can never understand, you will have difficulties without this next topic. ये बहुत important correlations हैं entropy से related which we will derive. ठीक है, सो ये मैं आपके साथ एक वीडियो लेक्चर शेयर कर लूँगा। ये न्यूमेरिकल भी काफ़ी ट्रिकी सा है, सो मे बी न्यूमेरिकल या लाइव क्लास में दोनों में हम इस न्यूमेरिकल को डिस्कस करेंगे नेक्स्ट वीक। ओके जी, सो नाउ